Let's apply the TDS equations to an ideal gas. And you may have already gotten practice with part of this problem on a worksheet, but we want to go through the whole thing in detail. So imagine that we're given that we have an ideal gas. Well, in general, one of the TDS equations that applies is, of course, TDS equals du plus PdV, everything lowercase except the temperature. For an ideal gas, there are two other relationships that we'll use. One is one form of the ideal gas law, PV equals RT. The other is the expression that relates the specific heat at constant volume to the internal energy and the temperature. That's CV equals du dt. Remember, for an ideal gas, this becomes a full derivative of u with respect to t, simply because you've eliminated 1 degree of freedom with an ideal gas also having the ideal gas law. Okay, so if we want to apply this to an ideal gas, we'll start with the TDS equation. And I'm going to rearrange this so that we're just dealing with ds. Now what we want to do is basically find substitute expressions for the two terms on the right. So one of those we'll be able to use the ideal gas law for, and let's just write down PV equals RT for an ideal gas. Well, we can rearrange that as P over T equals R over V. We can just substitute this into the second term on the right. Okay, so let's do that. That gives us d little s equals du over T plus R over V dV, and all of these v's are lowercase in this problem. Okay, so we'll move that up and keep that. Now we want to do something with the first term on the right, the du over T term. Well, now we can use the specific heat expression, so if CV equals du over dt for an ideal gas, then we can rearrange that to solve for du, right? So du equals C dt, substitute in du for the du in the numerator of that expression, and we get that ds equals now CV as a function of temperature divided by the temperature dt plus R over V dV. Just to be clear, the parenthetical t there is not multiplying by t, it is illustrating that CV could conceivably be a function of temperature. Okay, so now we'll integrate everything, and remember, if you want to integrate, you just want to go between state 1 and state 2, right? So we integrate everything from 1 to 2, but of course, the variable of integration has to change because it depends on the differential. So we integrate from S1 to S2 for ds, T1 to T2 for dt, and V1 to V2 of dV. Let's move that up. Now we can simplify this for the left-hand term, of course, that's just going to be S2 minus S1. And for the rightmost term, well, we know how to do that integral at least. We've seen plenty of logarithmics here, so it'll end up being the integral of 1 over V dV times R. That's just R times the ln of V2 over V1. That middle term, though, we have to be careful with. So actually, the most general expression we can come up with to solve this is S2 minus S1 equals that integral in the middle plus R ln of V2 over V1. Now, if we know that the specific heat is constant with respect to temperature, of course you can immediately pull that out, and then you'll have another ln, this time dealing with temperature. But generally speaking, you can't do that. For an ideal gas, you don't have a guarantee that the specific heat is a constant function of temperature. It may be that it does vary with temperature, as is indicated there. If that's true, then this is about as far as you can get. You would need to know the details of the function to solve this. You can use very similar steps to come up with the expression involving the specific heat at constant pressure and the logarithms of pressure to get this final expression. I'll let you handle that one on your own. The logic is exactly identical to what we just did. The difference is you want to relate the two specific heats, but of course for an ideal gas, that's easy to do.